Hello everyone, in this video I'm going to present our recent work, How does pseudo-labeling affect the generalization error of the semi-supervised Gibbs algorithm. I'm the speaker, He Haiyun. I'm currently a postdoc in Cornell. This is a joint work by me, Golamali from the Alan Turing Institute, Yuhen from the University of Florida, Miguel from University College London, and Vincent from the National University of Singapore. First of all, I'll briefly introduce the background of the Gibbs algorithm. For any learning algorithm, we can represent it using a conditional distribution PW given S. Thus, by looking at the well-known Gibbs posterior, we are interested in connecting it with the common learning algorithms. The Gibbs algorithm is given by the following expression, where alpha is the inverse temperature, pi is an arbitrary pi distribution of W, and F is the energy function. We denote it as the Gibbs algorithm. If we replace the energy function with the empirical risk in the learning problem, we find that, first, as the inverse temperature alpha goes to infinity, the Gibbs algorithm converges to the empirical risk minimization. Second, consider the Peck-Bayesian upper bound on the population risk over the true data distribution. If we let lambda equal to alpha in the left-hand side, that is the upper bound, and minimize this upper bound over all the possible learning algorithms, the Gibbs algorithm is actually the optimal one. Third, for the commonly used SGLD algorithm, where the factor of the Gaussian noise is a function of alpha, that is the inverse temperature, as the iteration increases to be large enough, the SGLD algorithm converges to the Gibbs algorithm. Thus, we believe that the Gibbs algorithm is a meaningful and tractable model for various learning algorithms. In the following, we aim to study the semi-supervised learning via the Gibbs algorithm. In our semi-supervised learning setup, we assume that we are given n label data, which is used to train an initial model W0. The label data are IID. The initial model W0 will assign pseudo-labels to m unlabeled data, where each unlabeled data is independent and follows the same distribution as the feature in the label dataset. Thus, we construct a pseudo-label dataset where the pseudo-labels are dependent on the label data. Together with the label data, the final output model W is generated by a conditional distribution PW given SL and hat SU. In this setup, for any non-negative loss function, the eta-weighted empirical risk is a mixture of the empirical risk on the label dataset and the pseudo-label dataset. The population risk is defined as under the true label data distribution, denoted by LP. The generalization error is defined as the expected gap between the population risk and the empirical risk on the label data. If the generalization error is high, it means that this algorithm tends to overfit to the labeled training data. We can then plug this total empirical risk into the Gibbs algorithm, and then we obtain a semi-supervised Gibbs algorithm. We can then theoretically analyze the generalization error under this semi-supervised Gibbs algorithm. Before presenting the main results, let us define some non-standard definitions, including the symmetrized KL divergence, symmetrized KL information, and the conditional symmetrized KL information. Especially the symmetrized KL information is the sum of the mutual information and the long-term information. In Theorem 1, we show an exact characterization of the generalization error for the semi-supervised Gibbs algorithm. The blue highlighted part represents the dependency between the labeled, pseudo-labeled data and the output model. The orange part represents the dependency between the labeled and the pseudo-labeled data. When the eta, that is the mixing parameter, goes to 0, which is equivalent to the case where there is no pseudo-labeled data, then the generalization error actually recovers back to that in the supervised learning setup. This results to better understand this Theorem 1, we derive novel upper bounds in the proposition 1. The blue part and the red and the orange parts play the same roles as those in the Theorem 1. The blue part can be written as follows, where we can see that the information shared between the W and the label dataset conditioned on the pseudo-label dataset affects the generalization error. If this shared information is high, then the generalization error is likely to be high. The orange part represents the information shared between the labeled and the pseudo-label datasets. If the pseudo-label data are highly dependent on the label data, then it will do harm to the generalization performance of the learning algorithm. The result shows a new perspective of understanding the effects of pseudo-labeling and can serve as a guideline for choosing an appropriate pseudo-labeling method in a semi-supervised learning algorithm. If we consider a special case where the pseudo-label data are independent of the label data, for example, the pseudo-labels are randomly generated, then we find that the generalization error actually corresponds to the result in this transfer learning problem. We can even extend our result to semi-supervised learning by entropy minimization without using the pseudo-labeling method, and we find that this expected generalization error is a function of the symmetrized scale information between W and SL given the unlabeled datasets. Moreover, we want to compare the semi-supervised learning with supervised learning with N plus M label data. So the generalization error for supervised learning with N plus M label data is given by this expression, and the semi-supervised learning is given by the following expression if we assume that the pseudo-labeling method is perfect, such that the conditional distribution matches the underlying conditional distribution. However, these two generalization errors are not necessarily equal with each other because the dependency on the label dataset plays an important role in the generalization error for the semi-supervised learning. We further obtain an distribution-free upper and lower bounds for the generalization error, where we first show that the pseudo-labeling degrades the convergence rate of the generalization error compared to the semi-supervised learning. And then we find that if the constant gamma is small, which means that the mutual information between the pseudo-labeled and labeled data is small, or the conditional mutual information between W and SL given the pseudo-labeled data is large, then it will lead to a tighter upper bound. We want to apply our theoretical results to an example that is the mean estimation example. In this mean estimation example, we assume that there are two classes of data and the conditional mean of each class is mu, but where the standard deviation is a constant sigma. We aim to estimate the mean of the data sets. We consider a square loss function and the prior distribution on W is to be uniform. Then the Gibbs posterior is actually a Gaussian distribution under this case. The expected generalization error is derived given by this following expression, where we can see that if the number of labeled and non-labeled data goes to infinity, the generalization error actually decreases to 0, and it's also dependent on the cross covariance between the labeled and pseudo-labeled data. If the trace of the cross covariance between the labeled and pseudo-labeled data decreases, then the expected generalization error decreases as well. To compare with the supervised learning case with N or N plus M label data, we find that if the cross covariance term is smaller than 0, then it means that the semi-supervised learning is the best option among the 3 learning algorithms. And if the cross covariance term is in between the 0 and the constant value of N, then the semi-supervised learning is better than the supervised learning with N label data. However, if the cross covariance term is too large, then the semi-supervised learning is even worse than the supervised learning with N label data, which means that it's not a good option to use the semi-supervised learning. To quantify the cross covariance term, we set the pseudo-labeling method to be a sign function. Then the cross covariance term turns out to be a non-negative value, which means that the semi-supervised learning generalization error is higher than a fully supervised learning. And we find that if we increase the number of unlabeled data to infinity, and there exists a gap between the generalization error of SSL and the generalization error of fully SL. In these figures, we show that the generalization error for the semi-supervised learning is in between the two supervised learning methods. And if the number of label data increases or the noise level in the data set decreases, then the gap between the semi-supervised learning and the fully supervised learning can decrease. To better understand our results, we find that we can even choose, based on our result, we can even choose an appropriate pseudo-labeling method. Consider the pseudo-labeling with threshold. That is, we only choose the pseudo-labels where the norm of W0 transpose X is greater than a certain threshold T. Then in this figure, we plot the different values of the cross-covariance term versus the threshold T, and we find that if we want to minimize the generalization error for the semi-supervised learning algorithm, we need to let T to be at least 7. So it means that our result can serve as a guideline for choosing an appropriate pseudo-labeling method among the given families. As we have mentioned, if we let the inverse temperature alpha goes to infinity, then the Gibbs algorithm converges to the empirical risk minimization. And under this setup, we can derive an exact characterization of the generalization error of the empirical risk minimization in semi-supervised learning, which is a function of the Hessian matrix of the empirical risk. If we let the loss function to be the negative log loss function, it is equivalent to the semi-supervised maximum likelihood estimation, and we obtain an asymptotic generalization error for this semi-supervised maximum likelihood estimation, which is a function of the Fisher information of the W lambda star. We can even obtain an asymptotic excess risk under this setup. The excess risk can be decomposed into the sum of the generalization error and the estimation error. Thus, in the asymptotic excess risk, we have a bias term, which is a function which represents the gap between the supervised learning and the semi-supervised learning, and also the variance term, which is similar to the generalization error. If we specialize to logistic regression example with regularization, we can obtain the expected generalization error, which is similar to the expression of the variance term in the excess risk. And we find that if we increase the lambda, that is the ratio between the unlabeled data and the labeled data, we find that the generalization error decreases and the variance term of the excess risk also decreases. However, the bias term in the excess risk increases. So there exists a sweet spot lambda to minimize the excess risk. It implies that there exists a lambda that can balance between this generalization error and the excess risk for a learning algorithm. To conclude, in our paper, we provide an exact characterization of the semi-supervised Gibbs algorithm, and then this characterization can be applied to obtain novel and informative upper and lower bounds. And our results show an insight that reducing the shared information between the labeled and pseudo-labeled samples can help to improve the generalization performance of the semi-supervised learning. And it can also serve as a guideline for choosing an appropriate pseudo-labeling method. We further analyze the effects of the ratio between the number of unlabeled and labeled data on the generalization error and the excess risk, using a mean estimation example and a logistic regression example. If you are interested in our work, please refer to our full text and feel free to contact us. Thank you.